Hello everyone and welcome back to the C++ 3D game tutorial series. In this second episode, we will see how to create the 3D graphics engine, which will allow us to render 3D graphics on our window using the DirectX 11 graphics API. As always, we will face three main parts: the requirements, design, and implementation of the software components required to create the graphics engine. Let's start with the requirements. We need a C++ IDE. In this series, we will use Visual Studio 2022 Community. The target platform is Windows. The target graphics API is DirectX 11. And last but not least, a good understanding of the C++ programming language is recommended. Now we can start the design part. In the previous episode, we started creating a minimalist game engine called DX3D. A minimalist game engine is a compact framework designed to provide the core features needed to create a game. These engines are typically code driven, giving developers direct access to the inner components of their projects and encouraging a deeper understanding of game development. Last time, we created the window using the Win32 API and introduced the entry point module of our game engine, the game class, along with the main game loop. This time, we will focus on developing the graphics engine. A graphics engine can be defined as a software component of a game engine, responsible for rendering 2D and/or 3D graphics on the screen. In software engineering, a component is a self-contained part of a system with a specific responsibility. Think of it as a building block in a larger system, in this case, the DX3D engine. At this point, a question comes spontaneously. How can we allow our graphics engine to render 2D or 3D graphics on the screen? Through the usage of Graphics API. A graphics API is a set of functions, classes, and protocols that allows software to communicate with the GPU to render images, 3D models, and animations on the screen. It provides developers with the functions needed to draw objects, manage textures and shaders, and handle resources required for visual rendering. In particular, in this tutorial series, we will use the DirectX 11 Graphics API. In order to have a clean and modular architecture, we should manage all the Graphics API related functionalities inside a suitable software component within our graphics engine. We will call this component the render system. A software component can be also defined as module or subsystem, depending on the context. A module is a smaller code unit like a file or class. A subsystem, instead, is a larger part made up of multiple components working together. For this reason, since our graphics engine is now made up of at least one software component with a specific responsibility, we can also define it as a subsystem. To sum up, the DX3D game engine is a software system composed of several key parts. At its core is the game, the entry point component of the engine, which manages and coordinates the various subsystems. The window module is responsible for creating and managing the game window. The graphics engine serves as a subsystem that provides the rendering layer for the game engine. Within it, the render system acts as a component responsible for managing the initialization and resources of the graphics API, in our case, Direct3D 11. Alright, let's dive into the next topic. In this episode, we will also introduce another important module within our DX3D engine, the logger, that provides a centralized way to print or output information, warnings, and errors in a consistent format in the console window. It's an essential tool for debugging and monitoring the behavior of our engine. It will be designed to support multiple verbosity levels, helping us control how much information we want to see at runtime. To tie the logger and other software components or modules together in a clean and maintainable way, we will apply the dependency injection pattern. Instead of relying on global singletons or tightly coupled dependencies, we will inject shared services like the logger into each class that needs them. This approach makes the relationships between systems explicit and transparent, helping us avoid hidden dependencies. In practice, we will use constructor injection, where we will inject dependencies through the parameters of a constructor. To keep our classes clean and avoid bloated constructors filled with redundant parameters, we will group them into simple descriptor structures and pass them through the constructors. This strategy is called dependency aggregation. By following these principles and structuring our engine around clear modular boundaries, we will build a system that is both robust and flexible. If you have any questions, doubts, or comments about this topic, feel free to leave them in the comment section of this video or on our Discord server. You can find the link to the Discord server in the video description. Also, if you find these tutorials helpful, please consider supporting their development on Patreon. Every contribution makes the difference, no matter the amount. Great, we have gathered all the necessary information to start the implementation. Let's start by introducing an important topic, the so-called Rule of Five. To better understand this concept, let's head over the game constructor. Here we are completely free to create a window object called win, and we can make a copy of it called w. What happens in this case? We create what's known as a shallow copy of the window object. A shallow copy in C++ means that only the top-level structure is duplicated, but not the dynamically allocated memory, handles, and so on. In other words, both the original and the copy share the same underlying resources. For example, in this case, we copy the Win32 window handle from the Win object into the W object. So we end up with two window objects that share the same underlying window. This is something we want to avoid, both for the window object and in general for all future components in our engine. To solve this issue, we can apply the so-called Rule of Five to the base class. But what exactly is the Rule of Five? It consists of implementing five specific methods in a class: the destructor, the copy constructor, the move constructor, the copy assignment operator, and the move assignment operator. In general, if our class manages resources manually, for example, the Win32 handle in the window class, and we need to implement at least one of these methods, then we should implement all five. In our case, we had already implemented the destructor, so we should have implemented the other four as well. By adding equal delete to the copy and move methods, we prevent this class and all its derived classes from being copied or moved in any way. In general, the resources in our engine will manage dynamically allocated memory and handles, so it makes sense to share this behavior across all the classes in our engine. Now, if we try to debug our code, compilation fails, because we are trying to copy a window object, which is now forbidden. So far so good. Let's go ahead and finally start creating our graphics module. With that completed, we can create the graphics engine class. To make file moving smoother, we can check the option Never Prompt before moving files to a new location. As usual, let's add our graphics engine class inside the DX3D namespace. Don't forget to inherit from the base class. An important note, here we are using the final keyword for the class. By doing this, we are preventing the graphics engine from being further derived by other classes. For now, we don't want users of our DX3D engine to extend the graphics engine class. Let's go ahead and implement the constructor and destructor as usual. Cool, we are now ready to implement the render system class. Important note, from now on, all the render system related resource files, both the header and C++ files, will be included in the source branch. This is to avoid exposing the Direct3D graphics API definitions in the public API of our DX3D engine. Again, let's include our class inside the DX3D namespace, inherit from the base class, and mark the class as final. With that done, we can implement the constructor and destructor. We are now ready to integrate the DirectX 11 graphics API. First, let's go to the project properties. Then, we can open the link list and access the Input tab. At this point, let's search for the Additional Dependencies field and edit it. What we need to do now is add the Direct3D 11 library called d3d11.lib. Once that's done, we can save all the changes. Now we are going to take care of the render system. Here we need to include the d3d11 header file, which provides all the class and function definitions of Direct3D 11. We are now ready to call the first and most important function of our render system, d3d11 create device. As the name suggests, this function allows us to create the Direct3D 11 device, for which we will be able to create all the graphics resources we need to render to our window. We need to pass a few specific parameters. The first one is the so-called DXGI adapter. A DXGI adapter typically represents a graphics card, GPU, installed on the system, although it can also represent other types of adapters, which we won't cover in this series. In our case, if we pass null as the first parameter and d3d driver type hardware as the second, Direct3D will pick the primary GPU. The next parameter expects a handle to a DLL that implements a custom software rasterizer. Since we are not using one, we can just pass null. At this point, we need to pass some flag values. Let's create an unsigned integer variable called createDeviceFlags. Here, we can combine multiple flags using the bitwise OR operator, the pipe character. In this case, we only want to add the flag that enables the Direct3D debug layer, which helps us get error and warning messages during runtime. What's next? The function requires a pointer to an array of feature level. By passing null, Direct3D will simply pick the best feature level supported by the system. For now, this behavior is good enough for us. The next parameter is the size of the previous array. Since we passed null, we can safely pass 0 here. Now that we have handled those, we need to pass the SDK version parameter. This is basically a safety check used by Microsoft to prevent version mismatches and ensure our program links with the correct Direct3D runtime. With that done, we move on to the output parameters. The first one is the most important, the Direct3D device. It represents the virtual GPU and is used to create and manage all the GPU related resources, like textures, shaders, buffers, and so on. We will explore these in more detail later in the series. For now, let's retrieve and store the raw pointer to the device in a suitable attribute. Let's add it to the render system class and call it the 3D device. Another important note here, just like we did previously with the window instance, we should use smart pointers. Unlike the window class, however, we can choose standard C++ smart pointers like unique pointer. Their 3D resources like the 3D device are COM objects, which use reference counting for memory management. Reference counting is a technique where each object keeps track of how many references or owners point to it. When a new reference is created, the count goes up. When a reference is released, the count goes down. When the count reaches 0, the object is automatically destroyed. For this type of object, we need to use COM_pointer, a smart pointer provided by the Windows Runtime C++ template library, which we can access by including the WRL header file. To pass the COM_pointer to the function, we can use the AND operator. This gives us a double pointer, which is what the function expects. The next output parameter is the feature level chosen internally by the function. Let's create a variable to retrieve and store it. Last but not least, we need to retrieve the so-called device context. We will explore this resource in future tutorials, but for now, let's get it the same way we did with the device. We have finally finished calling the D3D11 create device function. At this point, we need to check the return value so we can throw an exception if something goes wrong. In this case, we can use a handy macro called failed. Let's also include the core header file to use the runtime error exception. Alright, we have successfully initialized Direct3D 11. With that completed, we can finally go to the graphics engine class and instantiate our render system. As usual, let's use unique pointer. Since we need the definition of the render system class, let's add a forward declaration in the core header file. At this point, we can instantiate our render system by calling makeUnique, and we can safely include the render system header file in the C++ file without worrying about circular dependency issues. What we need to do now is instantiate the graphics engine inside the game class. Let's continue using unique pointer makeUnique to manage and instantiate the class. Pay attention here. The order in which we define the attributes is extremely important, especially when using smart pointers. In this case, when the game instance is deallocated, the first unique pointer that goes out of scope and gets deallocated is the window pointer, followed by the graphics engine. In other words, the last defined attribute is the first to be deallocated, and the first defined attribute is the last to be deallocated. Alright, let's dive into the debugging session. It seems to work. We have reached the render system constructor and the create device function seems to have been executed successfully. So what do we need to do now? We should double check that all the Direct3D resources have been properly released. A simple and immediate approach is to check the output window. If a series of DLL libraries related to a specific GPU driver, in this case the NVIDIA driver, have been unloaded, that could potentially indicate that all the Direct3D resources have been completely and successfully released. Of course, there are other more sophisticated ways to check this, but we will explore those in the upcoming tutorials. Now we are going to take care of the logger. So let's create the logger class and place it inside the core module. As always, let's include it in the DX3D namespace. Since we don't want users to extend it further, let's mark the class as final. At this point, we can add the constructor. We don't need to add a destructor since we don't have to handle any special attributes. By doing it this way, we are following the rule of zero, which states that we should not write any of the special member functions, so destructor, copy move constructor, or copy move assignment operator, unless we absolutely need to. Alright, let's create an enumeration called log level. An enumeration in C++ is a user-defined type that consists of a set of named integral constants. It's used to give meaningful names to sets of related values, typically integers, making our code more readable and safer. Also, by using the class keyword, we get a type-safe, scoped, and more modern enum. In particular, we want to create three log levels: information, warning, and error. Let's define a log level parameter in the logger constructor, and let's also assign it a default value, the error level. Here we can add the explicit keyword to the logger constructor. We should use explicit for single argument constructors to prevent unintended implicit conversions. So far so good, let's implement the constructor. With that completed, we can add a log level attribute to our logger class. And initialize it using the member initializer list. What's next? At this point, we can add the most important method of the logger, the log method. This method should accept the log level of the message and the message itself as parameters. Let's also declare the log method as constant by adding the const keyword at the end of the function signature. This tells the compiler that the function doesn't alter the state of the class, for example by modifying any attributes. So we are ensuring that calling this function leaves the class unchanged. We can now go ahead and implement it. First, the log function should behave as follows. If we set the level to error, we should print only error messages. If we set it to warning, we should get both warning and error messages. If we set it to information instead, we should get all types of messages. We can implement this logic using this simple condition. To print a message to the console, we will use an important object called clog, which is a standard C++ output stream. We can use it by including the iostream header file. What's next? We need to print some additional information alongside the message, specifically the log level. To do this, let's create a lambda function called logLevel2String, which takes a log level and returns the corresponding string. We can implement it using a simple switch statement. By default, we return unknown. In the other cases, we return the appropriate strings, so info, warning, and error. Alright, now we just need to print the log level string and the message. Let's also remember to add a new line escape sequence to move the output to the next line. With that completed, let's go to the game class. What we need to do now is create a unique pointer to the logger. Since it's currently the most foundational component of our engine, let's define it at the very beginning, so it will be the last to be released or deallocated. As usual, let's add a forward declaration of the class in the core header file. Now we can create the logger instance. And again, let's remember the attribute order. Let's create the logger as the first attribute. With everything in place, we can finally call the log method and print an information message that tells us the game has been initialized. Let's do the same thing in the destructor, printing a message that the game is shutting down. Don't forget to pass the log level as a parameter in the logger constructor. We want to see all messages, including formation ones. We are now ready to debug our program. As we can see on the screen, the console prints the information messages we defined earlier. These will be extremely useful in the next tutorials when we need to print debugging information like runtime values and so on. As a final step, let's also print the name or title of our program. Alright, let's dive into the next step. At this point, we want to provide access to the logger in all the classes of our DX3D engine, so that we can easily print log messages wherever needed. Of course, there are several ways to achieve this. One option is to use the singleton design pattern for our logger. A singleton is a class that allows only one instance of itself and provides global access to that instance. This kind of class could be useful, however, there are some important issues to consider. Any class can access it from anywhere, so it becomes hard to track dependencies. Code becomes tightly coupled to the singleton, and replacing it later or using it in other contexts becomes difficult. There are few cases, like the log, where singletons might be considered acceptable, but in general, it's better to avoid them. So, how can we provide access to the logger across all classes of our engine? By using a design pattern called dependency injection. Dependency injection is a design pattern where you pass or inject an object's dependencies from the outside. In particular, we will adopt constructor injection, a form of dependency injection where we provide a class's dependencies through its constructor. Let's proceed with this approach. First, let's go to the base class and add a non-null reference to the logger using the end character. By defining a non-null reference, we are enforcing the presence of the logger. This way, we can be absolutely sure that a logger is always available for all the classes in our engine. It also allows us to avoid checking whether the logger exists before using it. Now we need to pass, or better inject, this dependency, the logger reference, via the base class constructor. Before going further, it's important to understand that using the dependency injection design pattern can introduce some challenges. For example, if a class depends on many dependencies, we have to inject all of them, and as a result, the list of constructor parameters can grow significantly. Of course, this is not desirable. To avoid this issue, we can adopt a specific strategy called dependency aggregation. This strategy involves injecting a single object or structure that groups all dependencies together instead of injecting them one by one. Alright, let's create this kind of structure. First, let's create a common header file inside the core module. As usual, let's add the DX3D namespace. Here we can define the base descriptor structure, which will group all dependencies required by the base class. In this case, we have only one dependency, the logger, so let's add a non-null reference to the logger. Great! Now let's go back to the base class and update the constructor to accept a base descriptor as its parameter. Remember to pass this parameter by reference and most importantly, use the const keyword. This way we explicitly declare that the descriptor will be used in read-only mode. Also, let's make the constructor explicit, since it takes only one parameter. This helps avoid unintended implicit conversions. Great, we can now go ahead and implement our new constructor. Let's initialize the non-null logger reference in the member initializer list. Last but not least, let's add the getLogger method to retrieve the logger reference. Just a quick note here. We are declaring this method as constant, which means it doesn't modify the internal state of the class. We also use noExcept, which tells the compiler that the function doesn't throw exceptions. And finally, we use final to prevent the method from being overridden in derived classes. Alright, what we need to do now? We have to pass the reference to our logger to all the classes of our engine. Let's start with the game class. As we can see, near the member initializer list, there is an error. This happens because we are now required to pass the base descriptor in the constructor of our base class. To fix this, we can use brace initialization to pass the base descriptor. Now, we are also required to pass a non-null reference to the logger. We can safely reuse the makeUnique method we used previously. But there is a problem. We created a unique pointer to the logger, but here we need a reference, not a smart pointer. Not only that, we also need to detach the logger instance from the unique pointer. Otherwise, as soon as the brace initialization of the base descriptor finishes executing, the unique pointer will go out of scope and the logger will be deallocated. To detach the instance, we can call the release method. Then we need to dereference the raw pointer returned by release, using the star operator to get the non-null reference. So far so good. There is another issue though. Now the reference to our logger resides only inside the base class. So no one is managing its lifetime and no automatic deallocation will happen. Since we want the game class to be the only and unique owner of the logger, we can simply reinject the raw pointer back into the unique pointer. Alright, we are now managing the logger in a loosely coupled and modular way. What we need to do now is apply the same approach to the other classes. Let's go to the common header file and create the window descriptor structure. Here, instead of re-adding a reference to the logger, we simply include the base descriptor. In this way, we will be able to use it easily in the window constructor, and at the same time, we clearly and explicitly define the base descriptor as a component of the window descriptor. Let's repeat this same step for the other classes as well. At this point, let's go to the window header file and add the window descriptor as a non-null constant reference parameter in the constructor. As always, if the constructor has only one parameter, let's mark it as explicit. Let's implement it. Now we can easily pass the base descriptor to the base class via the member initializer list. Let's follow the exact same steps for the graphics engine and render system classes. Great, now our classes are ready to use the logger. Let's start by using it inside the Win32 Windows C++ file. For example, let's print an error message when register class X fails. Since we need the definition of the logger, let's go to the common header file and include the logger there. Of course, don't forget to include the common header in the window header file as well. Now we can finally call the log method. Let's do the same thing when create window X fails. Naturally, we should also log an error message when Dart3D11 initialization fails. To make sure everything works, let's try passing an invalid value to the create device function. One last thing, we need to pass the logger reference to all the remaining classes. So let's go to the game C++ file and pass it to both the graphics engine and window. At this point, we need to head to the graphics engine C++ file and pass the logger reference to the render system. Great, we have nearly finished. Let's debug our program. As expected, the create device function has failed and the logger correctly prints the error message. As the very last step, we should allow setting the log level from the game constructor. So let's go to the common header file and create the game descriptor structure. Here we can add the log level attribute. As we have already done previously, let's go to the game header file and pass the game descriptor as a parameter to the game constructor. Let's also mark the constructor as explicit. In the end, let's implement it. Finally, in the main C++ file, let's pass our desired log level. For this example, let's set it to info. Don't forget to pass the log level to the logger constructor. And while we are at it, let's also fix the invalid value we previously passed to the create device function. Now, if we try to debug it, everything should work properly. In this case, the logger prints all the messages, including the information ones. Let's test what happens if we set the log level to error instead. As expected, no messages are printed in the console window. That's all, folks. Today we learned how to start building our graphics engine. We also initialized the Direct3D11 graphics API. Furthermore, we created a logger to print useful messages and integrated it across the subsystems of our engine using the dependency injection pattern and the dependency aggregation strategy. In the next episode, we will start working on one of the fundamental parts of the rendering pipeline needed to render graphics on our window, the swap chain. I hope you enjoyed this video. See you soon. Thanks for watching.